So the last thing we're going to talk about with relation to solutions is what happens when we undergo phase changes with a solution, right? So with pure compounds, that's relatively easy. We just look at things like vapor pressure, we look at things like freezing point and all of that, and it more or less does what we expect it to do. When we have a solvent that now is part of a solution, though, the freezing point and the boiling point are going to change because we've changed the intermolecular forces that are in there. And intermolecular forces, of course, are responsible for phase changes. And so when we want to look at what happens to compounds or solutions, excuse me, that undergo phase changes, we need to look at what happens to the intermolecular forces. All right, I've got my pen going here. We are going to start. So these are called colligative properties of solutions. And basically what happens is that the freezing point, or the melting point, depending on how you look at it, always goes down, and the boiling point always rises. When we compare a solution, so this is, I guess, solution versus pure solvent. Okay. So if you have salt water, the freezing point of salt water is much lower. That's why we put salt on the roads during the winter, because water's freezing point decreases. So even though it's cold out, it's not cold enough to get to the freezing point, and so it remains as liquid water instead of ice. Right? The boiling point also rises. So if you've ever put salt in your pasta water in order to make it boil faster, that's not working. The boiling point is rising. You're doing that for taste. At least I hope so, as opposed to manipulating the boiling point. It doesn't actually make the thing boil faster. Okay, so in a solution versus a pure solvent, the freezing point will always lower, the boiling point will always rise. And so the question we ask ourselves is kind of, why is that? And the answer is that both of these, notice that in both cases, the solution wants to remain a liquid longer, right? So the boiling point, we're basically increasing the range that this solution remains a liquid, right? And both of these are a result of, both effects are a result of stronger solvent-solute interactions in comparison to the solvent-solvent interactions. Right? So remember that in order to make a solution, our solvent-solute interactions need to be the strongest force, because we need to essentially take apart that solute, and that means we also need to break the solvent up so that the solvent can interact with the solute. So anytime we're talking about a solution, we already know that we have stronger solvent-solute uh, intermolecular forces than solvent-solvent or solute-solute. So we already know that. So now we're going to use that to explain why our boiling point increases and our freezing point decreases. All right. And so because of that, when you get to the point where you are trying to make the phase change occur, right, what happens is that you have to, it requires more energy, right, higher temp, to break down the solvent-solute interactions. Sorry, that's kind of illegible, but hopefully you can follow that, right? And so that's why the boiling point rises. The freezing point lowers because basically it's harder for those molecules to organize themselves into a solid form where those intermolecular forces become strong enough to kind of hold them all in place. Because remember, in a solution, you've increased the entropy, And so going backwards and decreasing the entropy is actually very hard to do, and that's what a freezing point does. And so we decrease that down so that it can stay a liquid longer and all that. The formula, so now of course we want to know how much does the boiling point rise, how much does a freezing point lower. The formulas for these are actually pretty much the same thing, just different subscripts. So the change in boiling point temperature, right? So that's this whole term is one number, and this is the change in boiling point equals I times KB times M. Okay, so what are all these numbers? I is the Van't Hoff factor, and I'm not expecting you to know what that is. I'll come back to this and explain it, I promise. KB is a constant, right, that depends on the solvent. So this would be something that you'd have to be given, right? So you'll have a table of KB values, and then you choose which solvent you're using, and you apply the correct KB value. And the lowercase m is the molality of the solution. So if we go back a couple of videos, remember that we can calculate molality based on the moles of the solute and the kilograms of the solvent, right? So there's a few things to get to here. First of all, where did my thing go? First of all, I, right? I is the Van't Hoff factor. It's basically how many ions does your compound have? How many ions uh, in the solute, right? So if your solute is sodium chloride, right, you have sodium plus Cl minus, I for sodium chloride equals 2, right? If you use something like calcium bromide, calcium is a 2 plus, you have 2 Br minuses, and so the I value here would be 3. If you use something that's not ionic, like, I don't know, fructose or something, glucose rather, right, C6H12O6, there are no ions in here. All of these have a neutral charge, and so the I factor there would be 1. So basically you're counting the number of ions, so you're differentiating between ionic solids and covalent solids, right? That kind of thing. So the farther apart they are, the more likely they are to be ionic. Things like sodium chloride, calcium bromide are going to have larger Van't Hoff factors than the other ones. I'm going to do some examples of these in the next video, so I'm going to skip on to the next thing, and we'll come back to this idea of the boiling point elevation here in the next video, right? If we look at the equation for the freezing point depression, right? When the freezing point goes down, all right, it's not going to let me draw. 1 second. All right, if we look at the freezing point depression, it's exactly the same formula, except that, oops, darn it, not a T here, but instead a K. Is exactly the same expression, except that we're using freezing point data. So the freezing point is changing. Notice that the freezing point goes down, so we have a negative charge here. And we still have the same Van't Hoff factor. We still use molality. We just have a different set of constants for these kinds of things. So again, these K values, Kf, Kb, these will be given to you. Right? Those are not things that you'll have to calculate. Those are not things that you'll have to know or be able to figure out. Those will always be given to you. Okay. So freezing point depression follows the same rules, right? The number of ions, the molality, and the Kf factor. And the Kf factor is given, and again, it depends on your solvent. Right? So I might give you a series of Kf values, one for water, one for benzene, one for carbon tetrachloride, or something like that, right? And then give you Kf values for each one of those, and depending on which solvent you're using in your problem, you would select the right Kf value. Okay. So we've got a couple of equations. These are the things that are going to allow us to calculate how much of something, how much the freezing point is changing, how much the boiling point is changing, And the next video, we're going to actually do some examples of these and work some problems so you can see kind of how to manipulate these equations. What are the kinds of things they're going to ask? There's also 2 worksheets that involve these colligative properties because I think manipulating equations is one of those things that you can only get better at by practicing, right? You can watch me do it, but that doesn't really help you get any better. So A, watch me do it in the next video. B, definitely do those worksheets and practice them because they will help. All right, see you soon.